Okay, so welcome back to this week's lecture, and this is where we stopped in the last lecture. So, in the last lecture, I just briefly introduced to you about this particular architecture, the components, and why we need a software assembly language to actually enable that software programmable hardware capability, which is the essential differentiator for a microcomputer system or a microprocessor system. Correct? So now let's actually start learning about the functionality. Okay, so this is actually defined by us. It's not like this is universally, this should be the way a microprocessor system should work. No, not like that. We are, for the sake of building our 8-bit microcomputer, the textbook defines certain ways, and that is something like the way we will follow in this project also. Okay, so let's do that. So let's introduce or go through each one of these components, the significance. And interestingly, most of these terminologies are actually used in even modern day microprocessors that you see on your laptop or on your desktop, for example. Okay, so let's start with that. So I'll just go out of the slide mode. Okay, and we'll draw something for you so that you attend only to that particular section of this entire system. Okay, so that much easier to explain. But there's a small issue with the last video, recorded video, because the cursor was not really moving in that and was not captured. So sorry for that, but if you have any questions, we can discuss always offline. Okay, so let me go to the whiteboard and explain. Okay, so here we go. So the if you see the first step, basically, let me just open up in case. Okay, so we'll use black. Yeah, so the first component, which is actually an interesting component, is PC, and PC stands for program counter. Okay, so this terminology is being used even in modern day processors. So interesting, right? So the name itself actually conveys some meaning. So program counter, so it's counter which actually keeps record of the program. Okay, the basic instructions, the commands that you want the microprocessor to start doing. Okay, so let's say you switch on the microprocessor, it will actually take one by one the instructions in the program memory, the programs in the program memory, and executes one by one, right? So the program counter is a counter which keeps track of that. So as I said, this is just a counter that we studied in digital circuit, and we already know that. I'll just redraw the essential part of the circuit where this guy is dealing with. Okay, so obviously we have that 8-bit bus going like this. Correct, so there is an 8-bit bus, so let's always remember that this is 8-bit. But out of that, this guy, the PC guy, is actually sort of connected to this in sort of 4 bits, right? The reason why, what is the reason why 4 bits are used? Okay, so if it was a classroom session, it would have been more interactive, but unfortunately we can't do that. But you just pause the video and think why it is 4 bits. This is 8-bit bus, but 4 bits out of that 8-bit is only used and is coming out of program counter. That essentially means the program counter is counting from 0 0 0 0 to 1 1 1 1, because it's 4 bits, and this is connected to the memory, right? So before the memory there is some register which is acting as the input to the memory thing, right? So this is a 16x8 RAM, if you remember. Okay, you can always refer to the slide again, and this is MAR. Okay, so I will write all the abbreviations here. So MAR is memory address register. So as the name again suggests, it stores the memory of the address of the memory. So that's why it's a register which stores the address of the memory. This is a counter which records, or it's a pointer to the current instruction, right? It is actually generating that address. Okay, so let's put that way. Program counter generates an address. Okay, it generates an address between 0 0 0 0 and 1 1 1 1. So it goes in an incremental, right? It's sequential. Microprocessors are sequential operators, right? It executes one program after other, one instruction after the other. Like we saw in the last lecture, LDA is executed first, then add is executed first. So it sequentially goes. Whatever is written in your memory, it goes first address, then second address, and so on. So this produces that address. So let's say it starts when you reset. So basically, let me put some control signals to this. Obviously, there is a clock. Okay, so this is negative logic. So it's clock bar. Okay, so whenever the clock basically goes to 0, that edge, this will be triggered and it will increment the count. And then of course you need an basically a signal to make sure that only when this signal is signal is 1, then only when the program counter increments. Something like as when you design the counter, you have an enable, right? When that counter is enabled, then only the counting will happen. Otherwise, nothing will happen even if the clock goes on, right? So that's important. So CP is basically that particular signal which sort of increments the counter. So when CP is 1 and clock comes, counter increments. Otherwise, if CP is 0, whatever happens to the clock doesn't matter. The counter, whatever was the count earlier, will remain as it is. It will not change. So this is the basic signal that actually and it's like an enable signal to the counter which makes sure that counter is counting. Okay, and then of course, as I said, this 4 bits I think I hope you remember, this wire cannot be connected all the time, right? We need to have a control here. Whenever something is enabled, that controller is enabling it, then only these 4 bits will come to the bus. So we can't really connect it something like this. So we need a sort of a circuit which actually is a tri-state buffer, is something like this. So there is a buffer here and it has a control signal, and this is what actually in the figure, if you go back and see, they show it as EP. So enable the program counter to the bus. So EP is sort of enabling the program counter or connecting the program counter onto the bus. So it's 4 bit, don't forget that. So the 4 bits, the least significant 4 bits of this will get actually whatever values. The more significant 4 bits, whenever this is connected to the bus, is don't care, right? Don't care about it. So this is the program counter. So it is actually a counter which sort of has the address location, you could say, right? So it's, in this case, it's a 4 bit counter. So it counts from 000 to 1111, and some of the control signals associated with the program counter is it needs an enable, which is actually denoted in our case as CP, and then it needs an enable for making it connected to the bus, and that is EP. Okay, so whenever EP is 1, this guy, whatever content is here, will get connected to the bus. It's like a switch, you can say. So EP, this particular thing is like a switch. So whenever this is enabled, this switch basically bypasses, right? It's process, and this 4 bit will come here. So that's a thing. And now the program counter, as I said, is address of the memory, definitely. So it has to get here and it has to come to this. So this is actually again a 4 bit. And here actually again we will put that tri-state buffer after explaining. So this is again a register, and we know that counter can only count, it's a synchronous circuit. Obviously microprocessor or microcomputer is a synchronous circuit. It means that it only operates with a clock. So it is not an asynchronous circuit. That means asynchronous circuits can operate without a clock. Always remember that. All these are from your digital circuits. Okay. So synchronous circuit is something like it needs a clock for its operation, just like a heartbeat for us. Heartbeat is like a clock, right? We have a heartbeat and everything in our body functions based on that. So moment we stop heartbeat, the heartbeat is stopped, we are done, right, for the birth, right? It's gone. So similar to that, the clock is always needed. If you're not enabling the clock, if clock is not happening, there is nothing happening in this microcomputer or microprocessor. So important. Similarly, the register also has a clock. Okay, I think in this case it is just normal clock. So you can just say clock. Okay. Clock has this signature, right? So we have a clock here. So the same clock, here it's inverted, here it's not inverted. That's the only difference. And you can argue with me why it is inverted here. There's nothing like that. It's just for the sake of explanation in the textbook they put it this way, and I'm sure that in the textbook they want to optimize the operation. So that is why this is negative and this is positive. They want to make sure that every edge of the clock is utilized properly, because as a digital circuit person, as an engineer, you want to optimize everything, right? You want to get the maximum out of your circuit performance wise. So maybe for that reason this is inverted and this is not. Okay. So after you understand the full circuit, you can take a detailed look at why it is inverted and why it is not, and all those things. At this point you just accept whatever I am saying and follow it. And after, once you make a bare minimum circuit, you can always play with it. You can always change whatever you want. Okay. Just understand the essence of it, how it is working. Remaining is all for us to experiment. Okay. So this is it. So clock is needed here, again a register. So this register, actually one important aspect is this connection, right? We can't keep it connected all the time. So as we discussed, again we will have a buffer here somewhere in this case. So let me, and this directional in this way, and then this selection, if I remember, it is LM bar, load memory bar. So load L, basically the terminology that the textbook follows is, if the connection is from this guy to the bus is always shown by E. Okay, and P suffix is for the program counter in this case. Similarly, when it is from the bus to the register, okay, this way from the bus it is load L, okay, load, and then LM, M is standing for this memory address register. You can give whatever name you want, it doesn't matter. For simplicity, I am using as same as in the textbook. So LM is load to the memory register, EP is enable from the program counter to the, so E stands for from the register or the counter to the bus, and L stands for from the bus, load from the bus. That's a concept. Okay, so that's it. I think these are the control signals. LM bar and clock are the control signals for the memory address register. So you have the program counter, which actually keeps on counting as long as the CP is 1, but CP will not keep all the time 1. So we increment the counter, that value actually goes and sits in the memory register, and that doesn't solve our problem, right? That should point to the memory. So this should actually always get connected to the address. So this is the address of this particular RAM, and that is actually given from the memory address register. So whatever is the address coming here, let's say some example, I'm just taking an example. So let's say the address inside here is 0001, okay, for example. Then what happens is, this is a memory which has, we already showed it many times, it has so many locations, right? And this first location is always given by 0000, and last location is 1 by 1, all ones. And if this is the address which is given by memory address register, that is pointing to this address, and this is actually the data which is of interest to you. So that's what essentially happens. Let me clear it off. Sorry for the time. Okay, so essentially the important component, I'm just briefly explaining what all things are happening, then we will go in a logical flow using the slides. Okay, so it's important that you understand this concept clearly. So program counter is the one which has the sort of the address. In C language we can call something like pointer, right? So it has the address of the location which we are interested in. So program counter keeps on, it has the address of the program, okay, instruction which is to be executed. So this is the terminology which is used in modern computers also. So program counter is the pointer, is the address carrier of the memory of the instruction. So whichever instruction you want to execute next, that should be there in the program counter. Okay, and the program counter in this case, in this particular architecture, doesn't have direct access to the memory. It is gone through this. The reason is very simple, because we are using the same memory for data as well as program. Okay, so same memory is being used for program and data in our case, because ours is a very simple microcomputer. So we are using the same memory. So 16 locations are, maybe we can divide the first 8 locations for storing the program and remaining 8 locations for storing the data. Okay, so that's the critical aspect. So always remember that. There's no magic here. It's all very simple, and you should be able to understand it. Okay. So this guy will output to here, and then this will come memory address register, that will become the address of the location where you are interested in. And then the most important aspect is that data should go to the bus again. Okay, so this is the bus. So this is again 8-bit. Okay, and then of course this guy, whatever, so in this case, for example, I took an example, 0001 is address, so whatever is the content of that particular thing will get connected to the bus. We have to control again, we can't really always get connected, right? Always this memory cannot be connected to the bus, because bus is being reused many times, so you need another tri-state buffer here, which is actually shown like this, and this is shown by the name C bar. Again, some confusion. You use whatever name you want, okay, whichever makes sense to you. I'm just following textbook, but you can feel free to change the name of CP EP, LM, CE, you can give whatever. So this is CE bar, which again E stands for enabling this to here, and C stands for this memory thing. Okay. So this is, if this is basically, so this is negative logic, so I have to put this guy here. Even here also I have to put this negative. Okay. So when CE is 0, CE bar will become 1, and this will be enabled, and this whatever data which is pointed by this memory will get into this PES. So basically another switch here. So this switch open and off is determined by this control signal CE. Okay. So that's all we discussed. So this is how the program, whatever is there, will get loaded into the BES. So all we did is the circuit is there, and through some program like control signal, as well as I think only control signal, basically the values that you give to CPs, EPs, LM and CE bar will determine the connections. That's all. Okay. But the essence is program counter is where you have the address of the memory. It goes to the memory through the memory address register, not directly. The reason for that is the same memory is used for storing data as well as memory. So we can't directly bypass PC and connect it to RAM. If the memory for program and data was separate, you could have given a direct circuit. You don't need a memory address register. You can directly give that program counter output to this, right? So that's how you can make the circuit faster, but then you need an additional memory, so resource is more, so you lose out on the area. You have to have 2 memories, right, instead of 1. Okay, so those for the advanced stuff, or let's concentrate only for this particular thing. And now this is what essentially the initial components that is there. The other components that we have in that circuit was this particular thing, right? So as I said, when the memory has this, some data will be stored, and that 8-bit is actually, that 8-bit data is, for example, we had used it as LDA, I think let's give some address. So 1110. Okay, so 1110 is what? So this will be something like, if you remember, 8 plus 4 is 12 plus 2, 14. So this will be just before 15, right? So it will be not F is 1111, so this is E. And LDA we had, if you remember, it was 0000, so this will become 0. So 0E is what is stored. This is in hexadecimal. Okay. Okay, so basically LDA, that address is 00001110. If we group 4 at a time, this will stands for 0 and this will stand for E. So 0E is basically the instruction which is getting stored in this particular address, let's say. Okay, so this is how we store it in the memory to start with. Okay, we can't store LDA as we discussed. This is not understandable by machine. You have to convert it into binary, and this binary, for the easier expression, we store it as hexadecimal. Okay, but interpreted is inside it is treated as binary like this. Okay, so hope I'm not confusing. Okay, so this is basically something which is actually coming out and getting into the BES. That's what we discussed, and that's not the end of it, right? We have something known as, we have an instruction register. Okay, so IR. Okay, so IR stands for instruction register, and as the name suggests, it is actually the register which has the instructions, the programs which has to be executed. And where it comes from? This guy. Okay, so there is a connection like this, and as we discussed earlier, we can't directly give it, so we need to have a tri-state buffer again. Okay, and this will go here, and this is 8-bit. Okay, the same whatever 8-bit instruction is coming here will go and stay here. Okay, and this has a controller, and if I remember correctly, this is actually load, so it has to be L and I, LI bar, if I have a 0 here. Okay, so load from the data or the BES to the instruction register. That's why LI bar. So that's a controller which is actually controlling this. So this instruction will actually come and now sit in the instruction register, right? And again, this is also a register. For a register is a synchronous circuit again, so you need a clock. So again, this is actually a CLK. Okay, so there is a clock here, and then there is actually some. Now next is very important. Okay, the instruction register has 8 bits. Okay, so this is 8-bit. Let me just put the number. So this is again 4-bit. This is also 4-bit. Okay, so just remember that. So this instruction register has whatever content of memory which is coming and sitting here. So Now it is the most interesting aspect. So this instruction register has, if you remember what was the instruction, it was LDA E, right? EH, let me put H. H stands for hexadecimal. Okay, it's not a value, but it just means that E is actually hexadecimal representation. And we already know it, it was 0E, right? And this is 8-bit. It has two parts, this one and this one, or let me expand it, 00001110. So this guy and this guy, this is one 4-bit, this is another 4-bit. An instruction register has this together. Now what it does is, this guy is actually an address, right? It is, this E is actually an address of the data which I want to store in. So LDAE means, what is the, always go back to the previous lecture and understand, okay? LDAE means the physically what is going to happen, it has to load whatever data is in location E, location given by E, which is this one, 1110, into accumulator. Okay, so this one is an address. So the interesting aspect is this instruction register. Let me expand this bus. Okay, sorry. Let me expand this bus down. Okay, bus is just going down the same bus. Okay, so this instruction register, its output is again connected through a tri-state buffer. Okay, and only 4 bits. Why 4 bits? It's interesting because it's only caring about this. This is an instruction. This means LDA. It needs to issue control signals. Okay, so LDA has to issue some control signals so that our function does what, our computer does what, computer loads this content, whatever is content in this address, to the accumulator, which has to come here, right? Accumulator we are not drawn yet. So this instruction register, it takes input 8-bit, but then it splits that into least significant 4 bits and most significant 4 bits. Most significant 4 bit is the instruction, and that goes to the control unit. So this is the most significant 4 bit. So it goes to the control unit. We will take this last. Okay. So there is a control unit here, and the least significant 4 bit goes back to the bus. Okay. So that's the thing, and this has to be done through an enabling again, and it is actually to enable this guy to this guy. So this is E, I, that's it, and EI bar. So it again is a negative logic here. Okay. So LI bar will load data from the bus to the instruction register. EI will load the data, which is 4 bits, to the data bus. So the least significant 4 bits. The most significant 4 bit carries the instruction. What is the operation needs to be done? It can be LDA, it can be add, it can be sub, it can be out, it can be HLT, remember, and it can define anything more also, but we restrict only to these 4 operations, right? Yeah. So in fact, if we include this, these are the 5 operations that we are worried about, and this is the most significant 4 bits information. So that is going to the control unit, and based on these 4 bits, the control unit will issue all the necessary signals for this LDA operation to happen, or add operation to happen, or sub operation to happen, or out operation to happen, or halt operation to happen. So that's the thing. So we almost covered the left side of it. I hope there is no clarity issue. Okay. Now, as I said, this guy is actually carrying out the 4-bit address, and that will again go to this memory address register, and that will point to the address location 1110. So that is the reason why PC is not directly given to RAM, because this RAM has both program memory and data memory. The program memory is taken from the program counter, and the data memory is taken from the instruction. After the splitting, it just comes back and then comes as the comes again to the memory address register and points out. Okay, we will discuss this again, so don't worry. Okay. So that's the thing. And now coming back, so this memory, this basically last significant, this address will again go back to the bus, and it goes back to the memory address register, goes to the RAM. That data will get fetched out. Okay, now whatever data is there in 1110 will get fetched out, and where it has to go? It has to go to the accumulator. So we need to have an accumulator here. Okay, so I hope you remember the name accumulator. The reason is the result of any arithmetic operation is also getting into the accumulator. That's the reason why accumulator. So accumulator is again a register, 8-bit register. Okay, so let me just put 8-bit register. So it has an input. Okay, again through a buffer. We can't directly connect because that will create short circuit issues. So this is again a buffer, and since it is accumulator, and this is like loading to the accumulator, this will be LA, and this is again bar, so we'll have a not here, not operation here. Okay, so that's it. Okay, and then we have an add subtractor, which is a 8-bit add subtract unit here. So this is 8-bit, always remember that. You have to design that as part of the exercise. So, and this is one of the inputs which is coming out from here. This can be always connected. So this is 8-bit again. And then you have another register here, don't forget, because for addition and subtraction we have two operations. This is again 8-bit register B, and that is also connected to this accumulator. Correct? And always remember, this register also needs a control. So this is there again LB, right? Load from bus to the register B, LB bar. Yes, this is bar again. Okay, so that's done. And then these two contents will get added or subtracted based on our operation instruction, and the result will have to go back, right? The result will have to go back again through a buffer. We can't directly put because we can't directly connect all the time. So this is add, subtract, whatever name you want to. So here they have given it as EU enable, right? Because we need to connect the component to the bus. So E and U is the name they have given. You can give E add, subtract, whatever name you want. This is to basically control this operation. Okay. So this is one, means whatever result is there always will come back to the bus. Okay, so that's the case. And then of course we need to decide whether, okay, let's start from here. Some more control signals have to be done. One is the clock, because this is a register, so it needs a clock, correct? And then LA is there. And now similarly, for example, for the out command, whatever is the result in accumulator has to go to the bus and has to go to the output register. So there is a connection like this also, right? So we need to take the output of accumulator back to the bus. So we need a connector like this, and since this is EA, okay, so this is EA, not EA bar. Again, there is no reason why it should not be EA bar, but probably it will be an optimized way of treating it. So we will follow the textbook as it is. So this is EA. Okay, so these are the control signals. LA means this guy will get connected to this. EA means this guy will connect it back to the bus. That's it. So this part is done. And now for this is also a register, so it also has a clock. So always remember that. Don't forget to connect the clock, otherwise nothing will work. Okay, adder subtractor doesn't need a clock because it is a asynchronous circuit. Okay, very good. So that's it. And now here this is already there. There's no output from register B we are taking in this particular circuit, so we don't need an EB, right? There is no EB. Now one more control which is missing here is add or subtract unicide, right? So you have a control signal, let's say SU. So if it is 1, it will do add operation. If it is 0, it will do subtraction operation. That's a select signal for that. So I think almost everything is done. Now what is left is an output register. I think it's easy for you. So this is output register, again 8-bit. Again it requires a clock because it's an output. So this is a clock. And then of course we need a buffer circuit to take the input, right? So this will be L because it is loading from the bus, and this is LO, and this is also bar for you. Okay, so and this will be connected all the time to the display. Okay, so that's it. Okay, so I think everything is done. That's very good. So again I just reiterated that one by one without the help of any of the bigger circuit, right? So these are the essential components. So just to reiterate, we have a program counter here, which is a counter which counts from 0 to 15 in our case because it's a 4-bit. Okay, in our case address is 4 bits, the memory address only 16 locations which could be covered with 4 bits. That's the reason why program counter counts from 0 to 15. But now you can argue with me. Okay, now this is where your engineering thought process has to kick in, because here I said 16 locations, right? But 8 locations only for program or instruction. Remaining 8 locations we will reserve for data. So do we really require 4 bits here? Ideally speaking, no. If I am very sure that 8 locations are only used, I can reduce 1 bit here, it can be 3 bit. So we can design a 3-bit counter here to be exact. Okay, so but let's not go into that much of optimization at this point, but just wanted to trigger the thought process in you. So I always think about this. and it's always good you explore the circuit to the fullest so that you understand it. So the program counter has that. Memory address register has the address of the memory. So this sometimes stores whatever output is coming from program counter, sometimes stores whatever output is coming from the instruction register, right? So it stores both program as well as data address. That's why it's called memory address register, which points to the memory. In this case, we are using a 16x8 memory RAM, and then there is an instruction register which actually takes that instruction in and then splits that into the most significant 4 bits going to the control unit to issue the control signals. All these control signals, whatever you have, EP, CP, LM, CE, everything is control. You have almost like 12 bit or 12 wires to control. So 12 bits coming out of this. And then the remaining 4 bits again goes back to memory address register because that is address of the data. And that data will come out and either go to accumulator or register B. And depending on the operation issued, depending on the instruction, if it is add or sub or LDA, or in fact add or sub, this guy will be involved. If it is add, this control signal will make it as add. If it is sub, this control signal will. So basically, if it is sub or add, the control unit will issue those signals. Always remember that. Okay, so we'll come back. We'll have a sequential way of explaining this circuit. Then it becomes very clear. Okay, so depending on that, some result will come. Result will always get stored in accumulator again. So accumulator gets updated after every addition or subtraction. And then moment you want to display the output, you can enable the output register, store that data from accumulator to this, and then you get displayed. Right? So that's it. And now that's a beautiful aspect. Okay, so this is the circuit, and I think the time to stop here before we go into the actual functioning of the circuit. So next lecture it will be actual functioning of the circuit. So this was again sort of a refresher, a more detailed analysis from scratch how to build up this circuit. So just to make sure we understood everything, I'll just drag this to the side. So just to reiterate what we discussed. So the major components of our 8-bit microcomputer, or for that matter any modern day microprocessor, are, so you have a PC which is not personal computer, okay, it's program counter, right? So I'll just write so that you will again and again notice this program counter. 2, what is that? Program counter, what is that next? You give some name, MAR. So this may or may not exist depending on our requirement, but here we discussed. So memory address register, this is nothing but always stores the memory of the address location from where you want to take the instruction or data, depending on that. Okay, then you have a RAM, right? In this case we specifically used a 16x8. That means each location is 8 bits. So how many locations are there? 16 locations are there. Okay, so based on this, the program counter and memory address register values will change. So this is 16 locations, so we need 4 bits. So this will be 4 bit, this will be 4 bit. Then you have instruction register. IR is instruction register, right? Then you have 5, which is actually control unit, you can write, but I will just ignore it. You have the accumulator. Why the name accumulator is because the result of add subtraction also will get accumulated at the same register. So you can call it as register A, and to be more fancy you call it as accumulator. Modern day microprocessor doesn't have accumulator sort of thing, but it was there in all the microprocessors. So 6, you have of course this ALU or add or sub. So we have a very simple add sub unit, but you can expand it to a full-fledged arithmetic and logic unit, ALU, arithmetic and logic unit. And then you have a 7, which is actually another register, which is register B. And then you have 8, we have output register. So this is what we discussed. And then major component which you should not miss is the bus, right? We have only one bus here. The same bus is being used for data as well as address memory, and we already discussed what sort of architecture it is. Always remember that. I'm not going to tell the answer here. You always remember that. So it can be either Harvard or it can be, so one of those, right, if you remember correctly. Yeah, von Neumann or Harvard architecture. So you have to decide on that. How do you decide? Based on the whether you have separate bus for data and memory or you have single bus for data and memory. It's one of that. Okay, so please refer to the previous, maybe second lecture, and then you have the answer there, or first lecture in fact. Yeah. Okay, so that's done. So this is what I wanted to explain in this particular lecture. In the next lecture, we will uh, see how the entire process happens. What are the let's say let's put this way, whenever the clock ticks, okay, so each clock cycle there is something going to happen in this circuit. So we will define that, and that is the beauty, that is the lifeline, that is the way the microprocessor operates. So we'll discuss more details about that in the next class. Till then, it's bye from my side. Keep watching.